So now we're going to apply the concept of rank to the system, the linear algebraic system, AX equals C. This is a system of coupled equations that you've seen before, and in particular relate the rank to the linear dependence of the columns of A as it pertains to the existence and uniqueness of the solution. So for starters, let's look at the system AX equals C, and we'll interpret that as a stretching of the columns of A. So this is a concept I'd like to go over here. So if we have the matrix A, for example, and we'll say it's 1, 1, 0, 2, and we're going to multiply it by x, and let's just say x is 2 and 1. And we know that when we know how to do that multiplication, so this would be this top row times x, so this is 1 times 2 plus 1 times 1. And the next element of C is 0 times 2 times 2 plus 1, so that's 0 plus 2. And this gives C is equal to 3, 2. So one thing I'd like to point out is this is equivalent to multiplying the first column of A times 2, and actually let me use my white pencil for that. So that's the first column of A times 2 plus the second column of A, which is 1, 2, times 1. And so hopefully you can see that right here and right here. So this is 2, 0, 2, 0, and then 1, 2. And we can think of this as a vector, adding two vectors to give the solution 3, 2. So let me sketch this out sort of graphically. So we have x1, x2 space, and I'm going to label 1, 2, 3, 1, 2, 3. And so this is column 1 of matrix A, and this is column 2 of matrix A. And right, so column 1 goes over 1 and it stays, and x2 is equal to 0, so this is column 1. And column 2 goes over 1 and up 2, so this is column 2 of A. And when we multiply that by x, we're stretching column 2 by a factor of 2. So we're stretching it 2 times by a factor of 2. And in this particular case, for this is column 2, not column 1. And for column 2, we're stretching it by a factor of 1. So in this case, the product of x times column 2 is just itself. And then we're going to add to column 1 plus column 2. And when we do that, we put column 2, 1 times column 2 at the head of 2 times column 1. And so this is 1 times column 2. And the result is our column is our C vector, right? It goes over 3 and up 2. So we can think of AX as stretching the columns of A and producing a new vector. And so in general, for example, so what we did is we have C1 and C2, which makes up matrix A, and we have X1 and X2, and that's the same thing as C1 times X1 plus C2 times X2. So key concept here is that the columns of A define the column space. And we can denote that column space as the span. It's the span of the span of C1 and C2. And this is 2D space on the plane X1 and X2 in the above example. Okay, so in this example, the columns spanned, well, two directions in this 2D plane, and so all the possible vectors that you can make out of C1 and C2 lie on this 2D space. So another concept is that the rank of A, which we'll define as R, defines the dimensionality of the column space. And here, the rank of A was equal to 2. Okay, so the determinant of A itself was not 0. So the smallest non-zero determinant in this case had 2 rows, had 2 columns. So the rank is 2. And so this also shows that the dimensionality of the column space was 2. So these are some key concepts in general to remember. And of course, all possible solutions for C, C can only lie in the column space of A for the system to be consistent, right? So if we stretch A by a vector x, we can only get a new vector that lies in the column space of A, if the system is consistent. Okay, so let's go on to this really important theorem, which you should write this out, take notes on this, stop the video and take notes on this. And we're going to go over each of these points, and it has to do with the existence and uniqueness of the solution here. Okay, so we'll start off with an example of A is equal to 1, 1, 0, 0, 2, 0, 0, 0, 1. And then we're going to have a vector x that's, again, going to stretch the columns of A. And the final vector is 2, 1, 3. And so the task is to determine whether there is a solution, and if there is, whether the solution is unique. So let's look at the augmented matrix. And that augmented matrix is 0, 1, 0, 2, 0, 2, 0, 1, 0, 0, 1, 3. And we'll start off by reducing this. We'll go through the process of reducing it to row using Gauss-Jordan reduction to reduced row echelon form. And when we do that, and you can go through and verify this yourself, but when I do that, the answer I get is the matrix 1, 0, 0, 3 halves, 0, 1, 0, 1 half, and 0, 0, 1, 3. And this tells me, of course, that x3 is equal to 3, x2 is equal to 1 half, and x1 is equal to 3 halves. So we know that the system is consistent. We found that the system is consistent. And it has a unique solution. Okay, so we're pertaining to this. This pertains to this part of the theorem. So we have a unique solution. So let's look at the rank of A. So the rank of A, right, is the dimension of the smallest determinant that's non-zero. And if we took the determinant of A, we would find that it's not zero. But also if we reduced A, or the augmented system, using Gauss elimination, we would see if there's any zero rows, and there's no zero rows. And so we know that the rank of A is equal to the number of non-zero rows, so that's 3. And the rank of A is also equal to the rank of the augmented matrix, and it's equal to the number of columns. So in this case, there's only one way to stretch the columns to get C. So we've shown an example of this particular situation in the theorem. Okay, so let's look at another example, and we're going to look at a very similar matrix, A, 1, 1, 0, just like the last one, 2, 0, 0, 2, 0 on the second row, just as the same as the last one. But this one, the bottom row, is going to be all zeros. And we're going to again multiply by x, our stretching vector, and we'll look at the solution 2, 1, 0, and that was the is that the same? That was slightly different than our other vector C before. Okay, so let's look at our augmented matrix and reduce that using Gauss-Jordan reduction. So we can look at the solution. And when we go through Gauss-Jordan reduction, we come up with 1, 0, 0, 3 halves, 0, 1, 0, 1 half, and 0, 0, 0, 0. And this tells us that x1 is equal to 3 halves, x2 is equal to 1 half, and x3 is unconstrained. It's equal to alpha. So this is our free parameter, our one parameter controlling an infinite number of solutions. And so in this case, the rank of A is equal to 2, right? So we have a matrix that's already reduced, nearly already reduced by Gauss eliminations, since we have indented non-zero elements on the diagonals, and we have a zero row, and all zero rows or all zero columns are linearly dependent on the other rows and columns, and so we know that the rank of A here is only made up of non-zero rows, so that's equal to 2. And likewise, that's also equal to the rank of the augmented matrix, because again, we still have this, we have 2 rows in the augmented matrix that are non-zero, and this is less than the number of columns. And so if we have fewer than the number of columns, then we have P equals n minus r, in this case is equal to 3 minus 2 is equal to 1. So there's a P equals 1 parameters that control the family of solution. And it's a non-unique family of solutions. And again, the rank of the augmented matrix is equal to the rank of the original matrix, and that's less than n. And one way to understand this is if we look at our xy plane, x1, x2 plane, this defines the column space of A. But the unconstrained part of the solution lies out of the column space of A. So, oops. This goes in the x3 direction. And I'm going to show the x3 axis pointing up with a circle with a hole in it, as if you're looking at the tip of an arrow. The other thing is that C is in this plane, right? C is 2 and 1, so it goes over, well, 2 and 1. So C is in this well, it's in this plane. I'm not going to draw it because I would sort of go over my writing here, but C is in this plane. And so the reason we have a non-unique solution is that we can stretch x3 by any amount out of this plane and still satisfy the solution with the column space of A being in the plane. In other words, x3 can be anything, and we're still satisfying this equation. We're still stretching the 2 in-plane columns of A by x to get our C vector. So the other concept is that P is also to the dimensionality of the null space of A. And so the null space is the span of all vectors for which AX is equal to 0. The 0 vector. So in this case, when we have our matrix 1, 1, 0, 0, 2, 0, 0, 0, 0 times 0, 0 alpha, which is the vector only pointing in the x3 direction, we always get 0. So X, the null space, the first null, the null space of A is defined by this vector. And so the null space is equal to the span. We would write this formally as the span of X, well, the span of 0, 0, alpha. And the null space lies out of the plane, out of the x1, x2 plane, and it lies in the direction, I guess, going out of your page. And so this has again one parameter family of solutions. The null space is one-dimensional, extending out of this plane, and this solution is non-unique. And so that's this part of the theorem. Okay, so the last part of the theorem is the case in which we don't have a solution. And let's look at the same matrix that we looked at just now for A. And we have X again. And in this case, C is 2, 1, 3. And if we were to take our augmented matrix, 1, 1, 0, 2, 0, 2, 0, 1, 0, 0, 0, 3, and reduce that using Gauss-Jordan reduction, we would get 1, 0, 0, 3 over 2, 0, 1, 0, 1 half, and 0, 0, 0, 3. And what this says is x1 is equal to 3 halves, the same as the previous example. x2 is equal to 1 half, which is the same as the previous example. But in this case, 0 is equal to 3. And that's not true, right? That is, 0 is definitely not equal to 2. So the system is not consistent. And if we look at our matrices, so the rank of A is the same as it was before, is equal to 2. But the rank of our augmented matrix, this is our augmented matrix, is now 3. So we have 3 non-zero rows. And what this is saying is that this vector C is adding to the dimensionality of the column space of A. So remember, the columns of A, which was the same as what we looked at before, was in the x1, x2 plane. But C has a component that pops out of the x1, x2 plane, right? So there's no way to add columns, stretch the columns of A, which lie in the x1, x2 plane, to come off the x1, x2 plane into the third dimension. So the system is just not consistent. And so this represents the case if there's no solutions. And that's when the augmented matrix has a different rank than the original matrix. Okay, so I'm going to, I guess, hopefully finish up in the next couple minutes here. And we're going to look at a special case of AX equals C, where in this case, C is equal to the 0 vector. So this is a special case of AX equals C. So we know that the rank of A is equal to the rank of the augmented matrix, because with C is equal to the 0 matrix, this is linearly dependent on all columns of A. So it doesn't add to the dimensionality of the system. So C is, so we know the rank of A is equal to the rank of C. And so we know that the system is consistent from the previous theorem. And we know that for sure it admits the solution x equals 0. The 0 vector is a solution. And this is the trivial solution. And maybe you can think of it as trivial because when we multiply anything by 0, we get 0, okay? And so we know that the trivial solution is always a solution to the system AX equals 0. So that's this. And so let's look at this part. The trivial solution is the unique, can't check this off yet. X equals 0 is the unique solution if and only if the rank of A is equal to the number of columns. So let's look at that. So if we have, again, we're multiplying column 1 times x1 plus column 2 times x2 and so forth. And we know that that product is all equal to 0. And we know if the columns are linearly independent from one another, then the only way to get 0 is if these x's are all zeros. Sorry, this is not a vector x2. This is the second element of vector 2. And likewise, this is the second element of vector x, and this is the nth element of vector x. Okay, so if all the columns are linearly independent, then we know that all the x's have to be 0 for the right-hand side to be 0. And we also know that the rank of A is equal to the number of columns. Right? The rank of A is the number of linearly independent columns and rows, so we know the rank of A is equal to n. So x equals 0 is the only solution if that's true. And then for this last part, let's imagine if the columns of A are linearly dependent, then there are values of x1, x2, etc. that are not equal to 0. And so x1 not equal to 0, or the non-trivial solution, is available. So if there are linearly dependent columns, then the rank of A is less than n, and there'll be a n equals r parameter family of solutions that are non-trivial. And that's only if the rank of A is less than the number of columns. Right? Okay, so hopefully this is making sense. And so the last part has to do with the very special case when A is a square matrix. And like the case when A is not squared, it always admits a trivial solution. And it admits a non-trivial solution if the determinant of A is not equal to 0, or is equal to 0. In other words, the determinant of A is equal to 0 when the rank is less than n. right? So remember, the rank was the largest submatrix with a non-zero determinant. If the determinant of A itself is non-zero, then there must be a smaller submatrix, and the dimension of that smaller submatrix is less than n. So that's the case for a square matrix. Okay, so I guess I'll conclude this video here on the rank and its application to the system AX equals C.